So benzene ring. Remember that this is it's an aromatic compound, right? And this goes back to aromaticity, and in order for a molecule to be aromatic, it needs to meet 4 conditions. It needs to be cyclic, it needs to be planar, it needs to have the Huckel number of electrons, and that's right, 4n plus 2 rule. Alright? And there was one more, which was it needs to be conjugated. Do you remember something like this? Okay. Got all these guys. So okay, so now the end goal of this is that whatever meets this criteria, whatever molecule compound that meets this criteria, we say it's aromatic and is really stable. Right? Another way we can say that something is stable is that we can say that it's not really reactive. Right? If something is unstable, it's reactive. If it is stable, it's not reactive. If it's unstable, it's reactive. So it's not reactive. So therefore, the benzene ring is not reactive. The benzene, normal benzene, because of the whole concept of aromaticity, which you guys talked about, it's not all that reactive. Right? So that means that if we had a normal double bond like this, and if we did HBr, HX addition, we would get Markov-Nikov addition of the Br here, right? Organic one. However, if we did the same thing on the benzene ring, because of that whole concept of aromaticity, we would get no reaction. Because the benzene ring is more stable than this. So it's not going to react. Make sense? Okay, now let's analyze this a little bit further. What role is the double bond playing in this reaction? What role is this double bond? Is this my nucleophile or is it my electrophile? Okay, it's okay. This would be my nucleophile because of the pi electrons. If I'm a nucleophile, I'm electron rich. Right? If I'm an electrophile, I'm electron deficient. So this guy has this pi electrons, so it makes him electron rich. And there's a polarity here, right? Partial positive, partial negative. This guy here is going to be my electrophile. Perfect. Excellent. So in any reaction, we're going to have a nucleophile and we're going to have an electrophile. And what's going to happen is that the nucleophile is going to donate the electron to the electrophile, and we're going to form a bond between the nucleophile and the electrophile, and that's our product. This is how reactions usually occur, and you got to be able to identify who is my nucleophile and who's my electrophile. So when the benzene ring reacts, right? Okay, if in this case here, it would be no reaction, right? But this benzene ring, it should be acting as a nucleophile. Perfect. And this guy here should be acting as an electrophile, because the bromine is pulling away the electron density from it. So therefore he becomes electron deficient, because the bromine is electronegative. So it likes. Yeah, you can see it that way. Okay. So in the in other phases of the reaction, you will see it behaving as a nucleophile. Another phase of the reaction. So, like for example, here I'll give you an example. So, let's say we wanted to show the complete mechanism of this reaction. We wanted to show the complete mechanism of this reaction here. Alright, so we start off with this. Cool. And we react it with HBr. This is going to donate electrons here. This is my nucleophile, donates electrons to my electrophile. This bond snaps. I'm going to form a carbocation. I can form 2 carbocations, but I want the more stable one, so I want the one here. Perfect. And then the bromine here, negative. My electrophile, electron deficient. Nucleophile, electron rich. Nucleophile donates electrons to the electrophile. They form a bond, and I form my product.
Everything is based on interaction between nucleophiles.
It's always this way. And the arrows always goes from the nucleophile to the electrophile. Always.
Okay. See, I never knew.
If you saw that, your life would have been a lot easier, right?
Yeah, no, I didn't do that.
Your life would have been easier. I understand.
Yeah, I mean, they show us how to do everything.
Yeah.
You learn direction, right?
Okay. So you're gonna learn a lot of the whys.
Okay.
Okay, so I want to give you the why between the EAS reaction and why this stuff is happening. So we have a nucleophile, and this nucleophile is our benzene ring. Okay, now imagine this, right? If I'm a nucleophile, what must I be? I must be electron rich. If I'm an electrophile, what must I be? Perfect. So that means now if this is a magnet, if I have 2 strong magnets, then their attraction is going to increase, right? So if I have a really powerful nucleophile and a really powerful electrophile, the reaction would want to occur. Now, it's true that this reaction is not occurring, but there's a way we can force it to happen. And the way we can force it to happen is if we can create a stronger electrophile. That's the whole purpose of EAS reactions. The whole purpose of EAS reaction is that the benzene ring is too stable. It doesn't want to react like a normal alkene. So now what we want to do is make that electrophile more potent. We want to make it stronger so that it will be willing to react with a stable benzene ring.
So make the electrophile more efficient?
More potent, like make it more electrophilic.
Okay.
And when we make it more electrophilic, it will now want to react with the benzene ring.
Okay.
It's because the whole aromaticity messed up the benzene ring. So it's so stable that it doesn't want to react like a normal double bond.
Okay.
But if we can get a stronger electrophile, then it's going to be willing to react with the benzene ring.
Okay.
So that's the whole purpose of EAS reaction. The whole purpose of the EAS reaction is to create a stronger electrophile so that the benzene ring will be willing to react with it. Alright, so now this stands for, what does the E stand for?
Electrophilic.
Yep. And how about the A? Arrow. Perfect. Cool. Alright, now in this reaction we're going to have a benzene ring and we're going to have an electrophile substituting for hydrogen. Alright, this here is going to be substituting a hydrogen on the benzene. So what we're going to do, we're going to start off with a benzene ring. Because the normal electrophile that we would use is not good enough, we have to create a stronger electrophile. Now it's going to be willing to react with the benzene ring. And what kind of reaction is it going to do? It's going to do a substitution reaction. So that means that something will replace something else. In a substitution reaction, something gets replaced by something else. In the EAS reaction, we're simply going to have a benzene ring, and one of the hydrogens is going to get replaced by an electrophile. Right? And this here is called a mono substitution. Right? Now, mono substitution just means that we've only added one electrophile. We've only substituted one.